Hello students, this is Dr. Munir Omar with the Database Management Systems CS222. Today we will study about functional dependencies. Actually, this topic is about the association among attributes in tables. These are the contents for today's lecture. First, we will study about the functional dependency. Then the functional dependency and keys. After that, we will have a look into some rules associated with these dependencies, and these rules are called inference rules. And inside this topic, we have some types. These are reflexivity, augmentation, transitivity, additivity, projectivity, and pseudo transitivity. So we will study all these in today's lecture. Actually, all these are associated with the association among different attributes of database tables, and these all are required for the normalization of data in the database tables. So before starting the functional dependency, I want to let you know that we need this functional dependency mainly for the process of normalization. As you know that normalization is the process of minimizing redundancy from a relation or a set of relations. We have already studied about database anomalies in our previous lecture, which was about the issues which we face due to redundancy in the databases. And we also studied that the solution for database redundancy or data redundancy in databases is the normalization process. So normalization is actually based on functional dependencies, and functional dependency is actually a type of relationship between attributes of a table. So the first thing is functional dependency. Suppose we have a relation R or table named as R, and it has two attributes A and B. So then we can say that attribute B is functionally dependent on attribute A if each value of A in R is associated with exactly one value of B, written as A determines B. It means that if we know the value of A, then we can precisely determine a unique value of B. Now, let's check this definition with a table. We have a relation R. It has two attributes A and B. Let's say this is the table, and this can be called as R. And let's say here we have two attributes, attribute A and attribute B. Now, here, if you take this MCS and look into the value of attribute B, then it would be 64. Similarly, for BCS, the value of program credits or attribute B would be 132. So we can say that this program name determines the program credits. If there is MCS anywhere under A, then under B it would be 64. We can say that A determines B or B is dependent on A. So this thing is called functional dependency. Suppose here we have a relation R. We can also call this thing as a table, and it has some attributes, and there is some sort of functional dependency among these attributes. Here A determines the attribute B, C, D, and D determines the attribute D itself and E. So these attributes are either determinant or dependent. Attribute or set of attributes on the left side here are called determinant, and on the right side are called dependent. Here we have a functional dependency. A determines B and C. So A is determinant and B, C are dependents. This can be any sort of table. For example, we have a table for student. So we can say that student ID determines the name of student and father name of student. So this is the example of student table. Here we have a student table. It has ID, name, uh, student address, parent name, program name, and credits. There are two functional dependencies. In the first case, student ID is determining the student name, student address, program name, and credits. It is like if we have the ID of a student, then we can get information about his name, his or her name, the address of student, his program name, and also the credits offered in that program. And there is another functional dependency that is about the program. So if we have the program name, then we can get the credits of that program. So here student ID is a determinant. It determines the student name, student address, program name, and credits. And similarly, the program name is determining the credits. These on the right side are dependent, and these, the student ID and P name, these are determinants. This is the table for previous example. Then we have functional dependencies and keys. We can determine the keys of a table seeing its functional dependencies. If we know about the functional dependencies among these attributes, then we can also get, or we can guess the keys of this table, that which attributes are associated with one another. So it would be quite easy for us to get the keys from this table once we know the dependencies among these attributes. The determinant of an FD that determines all attributes of that table is the super key. Now in this case, this student ID is super key because it determines all these attributes. So once we know this fact, then we can easily identify the super key. Then the minimal super key is the candidate key. So if a determinant of an FD determines all attributes of that relation, then it is definitely a super key. So if we have a super key, then definitely that would be considered either primary key or candidate key. So if a determinant determines all the attributes of that table, then definitely that would be a super key. Here we have an example of employee table. We have a table EMP used for employee. It has some attributes. The first one is employee ID, then name, employee address, department, project ID, and project salary. Actually, these employees are working in some projects. So for each employee, we are also identifying the project and the salary in that project. So there are two functional dependencies. First, by taking the employee ID as a super key, and second, by taking the employee ID plus the project ID for determination. So if we take the employee ID, it determines the name, department, and address of employee. And if we take a composite of employee ID and project ID, then we can get the project salary of that employee. So here we have two functional dependencies in this table, and we can determine the keys according to these functional dependencies. Then we have another table that is about student, student ID, student name, program name, address, NIC, and CGPA. These are the attributes of student table. And if we look into this table, we can find some dependencies. Here, the first one is about student ID. It determines the student name, program name, address, CNIC, and CGPA. And similarly, the NIC is also determining all these attributes. So here we have two attributes, and both are candidate. Both can be used as primary key in this table. Then we have inference rules. These rules are called inference exams or Armstrong exams. These are rules that establish certain functional dependencies from a given set of functional dependencies. Actually, now these dependencies are of different types. So we can specify the type with the help of these rules, and we can also expand these functional dependencies, and we can get some new functional dependencies with the help of these rules. The first one is reflexivity. In this type of inference rule, actually, we uh, deal with the attributes in a way that it determines itself or a set in which it is present. Here we have an example. If we look into the example, the student name and student address both are composite, and these both are determining the student name. So this student name is present at both places. So we can assume if there is a composite key, then it must determine its part. Similarly, the student address will also determine itself. We can also create one another functional dependency where we can type the student address here instead of student name. That will also work. B is a subset of A, then A determines B. So here we have a composite. This can be called as A, and let's say this part is B. This is subset of A. So if we have A, B is subset of this A, then this will also determine B. Similarly, this rule implies that an attribute can be used to determine itself. Here, student name determines itself, so this is also possible according to the reflexivity inference rule. Then we have augmentation. If we have A determines B, then we can also add one additional attribute on both the sides, and that will also work. So if A determines B, then AC will also determine BC. For example, we have student ID and it determines student name. So if we composite the address with student ID, this will also determine the student name and student address. So here this address is used on both sides, and according to this augmentation rule, the condition will be correct. Then we have transitivity. If A is determining B and B is determining C, then A will also determine C. This is actually the transitivity. If one attribute is determining second and the second one is determining third one, then the first one will also determine the third one. So here we have example: if student ID determines the program name and program name determines the credits, then we can assume that student ID can be used to determine the credits. Next we have additivity. If A determines B and A determines C, then we can also assume that A will determine BC. Here we have an example. In a table we have employee ID and it is determining the employee name, and also the employee ID can be used to determine the qualification of employee. So this can be written as employee ID determines the employee name as well as the qualification. Then we have projectivity or decomposition. Here we say that if A determines BC, and according to this rule we can assume that A will determine B as well as A will determine C. It is actually the inverse of previous case. Here we combined two attributes according to the given functional dependencies, and here we are going in reverse. We are splitting the attributes and making some new dependencies. So here we have employee ID and it is determining the employee name and qualification, and this can be decomposed and two new functional dependencies can be created where employee ID will be used to determine the employee name and employee ID will be used to determine the qualification of employee. So this thing is also possible according to the projectivity or decomposition inference rule. Next we have pseudo transitivity. If A determines B and CB determines D, then AC will also determine D. So here if you look into these values, we can see that this B is replaced with A. So this is pseudo transitivity. Example: student ID determines the student name according to A determines B. Then student name and father name determines the student address according to this one. Then according to these two we can get a new functional dependency that would be student ID and father name determines student address. So here if you look into this student name is actually replaced with this student ID, and here the A was replaced with B in the second case. So let's revise these rules with the help of table. Here we have a table. It has some records for student. We can check these rules in this table. So here the first one is reflexivity. B is a subset of A, then A determines B and B also determines itself. So in this table, let's say we have student ID and program name. These two are composite and these two are determining the program credits. So in this table we have a composite student ID and program name. So this composite can be called as A, and we can say, according to the rules, that the student ID plus program name can determine student ID, or the student ID plus program name can determine program name. So student ID plus program name, this is a composite, and this composite can determine its parts. Similarly, the student ID can also determine itself according to the first rule, that is reflexivity. The second rule is augmentation. If A determines B, then AC also determines BC. So here student ID is determining, let's say, student address. A determines B, then AC will also determine B. So if we add this student name with student ID, then this composite will also determine the student address according to the rule. Then we have third rule, that is about the transitivity. If A determines B and B determines C, then A will also determine C. So here in this table, let's say student ID is A. It is determining the program name, which is B according to our definition, and program credits are C. So if we know the student ID, then we can get the program name of that student, and if we know the program name, then we can get the credits of that program. So student ID is determining the program name, and program name is determining the program credits. According to these functional dependencies, we can get one additional functional dependency, that is student ID determines the program credits. This is called transitivity. Student ID determines program name determines the program credits. So according to these, we can assume that the student ID will also determine the program credits. After transitivity, we have additivity or union. So if A determines B and A also determines C, then A will determine BC. So according to this table, here student ID is determining the student name, and student ID is determining the student address. This is, let's say, A, this one is B, and this one is, let's say, C. So A determines B and A determines C. So we can get one additional functional dependency, that would be A determines BC, means student ID determines student name and student address. Then we have the reverse of additivity, that is projectivity or decomposition. Here we go in reverse. If A is determining BC, then A will also determine B and A will also determine C. So here A is determining B and C, student ID is determining student name and address. Then we can also type these in a separate way by putting two additional functional dependencies, that student ID determines student name and student ID determines student address. This is decomposition. Then we have zero transitivity. If A determines B and CB determines D, then AC will also determine D. Here we assume that if we have student ID, then we can get the name of that student, and if we know the name of that student and address of that student, then we can get the program name of that student. So according to our assumption, student ID determines student name, or simply say A determines B, and student name plus student address determines program name, or B, C determines D. So we have two functional dependencies, and we can get one additional functional dependencies according to the rules. That would be student ID plus student address will be able to determine the program name. First, student ID determines student name, then that is A determines B, then student name plus student address determines program name, BC determines D, and after that we get A, C determines D, that is student ID plus student address determines the program name. So in today's lecture, we studied about the functional dependency, then functional dependency and keys, then inference rules, and we looked into some examples. I hope you will also explore this topic by yourselves. And if you have any question, you can put your comments in the KCMS. Thank you.